now. All right, welcome everyone to today's NBIA Astroparticle seminar. Today we're happy to have Bradley Kavanagh from the Cantabria Institute of Physics. Bradley did his PhD in Nottingham University, then he was a postdoc at a PhD in Saclay. Then he was a postdoc at Grappa in Amsterdam, and now he is at Cantabria. And he has worked prolifically on a variety of topics related to dark matter, both in direct and indirect detection. So for instance, local dark matter velocity distribution, on the Earth scattering effects on direct detection, and testing different mediator and models in direct detection, directional detection of dark matter, using neutrino telescopes to probe dark matter, and recently also paleo detectors. And today he's going to talk to us about an adjacent and related topic of his, which is black holes and their connection to dark matter. He was recently an author of a roadmap to using black holes and gravitational waves to test fundamental physics. And he's worked also on primordial black holes as tests of dark matter. So we're going to hear about that today from Bradley. So Bradley, thank you very much, and please take it away.
Thank you very much for the introduction, for inviting me, and thank you for kind of summarizing my prolific work on a number of different topics. It's sometimes hard to tie those things together, and I think in a second I might be able to explain how this ties in with that range of different topics. So yeah, thank you very much everybody for coming. I'm going to talk today about dark matter and black holes, and what we can learn about the dark matter that might be around black holes with gravitational waves. Okay, and like any good astroparticle physics talk, we should probably start off by acknowledging the collective pain that we feel that we haven't found a dark matter particle yet. Okay, and maybe this is where a lot of my other work has been based on so-called direct searches for dark matter, where you build a detector on Earth or nearby, and you hope that the dark matter passes through and you can detect it. And these haven't been successful so far. And so we perhaps have to start thinking about alternative directions, new ways that we can detect and probe dark matter that perhaps don't involve building terrestrial detectors. Okay, but let's start from a very zoomed out perspective, and that perspective is just that we know on all scales of the universe that there must be dark matter. Okay, so we know on the very largest scales, we know from the shape of the cosmic microwave background, the shape of the temperature anisotropies, that we need some non-baryonic matter content in the universe. Okay, and in particular, we need this dark matter to clump and to form structures early, so that baryons can fall into those gravitational wells and begin to form structure. Okay, and so then if you zoom in, some of the biggest bound objects in the universe, galaxy clusters, are also some of the most dark matter dominated. Okay, and so these are the large structures which are formed from baryons which have fallen into these dark matter wells. Okay, and we know from measurements of weak lensing and measurements of the temperatures of these clusters that there has to be quite a lot of dark matter that we just don't see. We can zoom in again at individual galaxies that live in these clusters, and you can see that the rotational velocity of these of the stars in these galaxies remains roughly flat as you move away from the center. Okay, and that's not what you would expect if you just had a central mass distribution, but instead this is what you would expect if you had a much more diffuse and larger halo of dark matter, which you don't directly observe. Okay, and we can do I think one or two more zoom in steps, and so the next zoom in step is looking for dark matter in our own galaxy. And we know from estimates of the motion of stars nearby that there must be some amount of dark matter within the solar system, within this room, within the room where you are right now. And for our purposes, this number is not, the exact value is not super relevant, but the important thing is that it's not zero. Okay, and so if we're here on Earth, we should be able to detect particles which pass through. Okay, or at least there should be particles which we might be able to detect as they pass through a detector that we build on Earth. Okay, the problem is that we haven't found those particles yet. And so let's pick a concrete example. I mean, there are plenty of examples of dark matter particles. Okay, you might be interested in WIMPs or in ultralight dark matter. I'm going to talk very briefly about so-called axion dark matter. So these are light scalar particles. Okay, and the typical mass range that we might be interested in is sort of electron volt down to micro electron volt for these particles. Okay, and they're very useful because they're one way that you might solve a number of problems in the QCD sector, the so-called strong CP problem, which explains why the neutron doesn't have a dipole moment. Okay, a magnetic dipole moment, electric dipole moment, sorry. Okay, and so there's this nice, well-motivated particle, and you think, well, it's all around us, and so maybe we can detect it. And for axions, it turns out that there's a coupling between the axion A and the electromagnetic field strength tensor. And so what that means is that in a strong magnetic field, an axion should be able to convert into a photon. And so what you can do is you can go away and build a number of different detectors and use these detectors to search for axions with a specific mass and probe down to different values of this coupling strength here, Ga gamma gamma. And nothing has been found using those techniques. And you can go further and you can think a little bit more indirectly. You can look at emission from X-ray emission in astrophysical systems, things like that. But we haven't found this particle yet. Okay, and that's the source of this frustration, this agony, that it feels like we should be able to find it. It's traveling through us. It's throughout the universe. How do we find these dark matter particles? And this is where gravitational waves comes in, because we now have an extra way, a new way of trying to look for these particles. Okay, and so gravitational waves are produced whenever you have a time-varying mass quadrupole moment. And so what that means is you just have a particular distribution of masses which is changing in time. And the most common one, and the one that we think about most often or most easily, is two compact objects orbiting around each other. Okay, and so every year when I give a talk like this particular plot, which shows the known black holes and the observed gravitational wave signals from the mergers of those black holes, this plot just gets more and more packed. Okay, and so each of these pairs of blue points is two black holes which have merged to form another black hole and which have been observed by the LIGO-Virgo detectors. Okay, and now we have LIGO-Virgo CAGRA. Okay, and so what this does is it gives us a different tool, a different thing that we can use to see the universe. And the question is, how can we use this to look for dark matter? And like Mauricio was saying, we wrote this kind of white paper a couple of years ago, thinking about all the ways you could use gravitational waves to probe dark matter. Okay, and so each of these kind of bars indicates a different way of probing dark matter, and the colors tell you whether we're thinking of current interferometers like LIGO, which is an Earth-based detector, or whether we're thinking of something more in the future, or whether we're thinking of very low frequency gravitational waves that you would detect with pulsar timing arrays. Okay, and as you can see, each of these different things, taken together, all these different probes span a huge range in dark matter mass that you might be able to probe. And this is really cool. You have to think carefully, and you have to decide exactly how you're going to look, which mass range you're going to look in, and exactly what signature you're going to look for. But this, to me, tells us that gravitational waves are a very exciting and interesting way to look for dark matter. Okay, and the thing that I'm going to talk about today is what's called dark matter dephasing, or gravitational wave dephasing. Okay, and I'll explain exactly what that is in a minute. But as you can see, it really covers a huge range of dark matter masses. Okay, and so it offers a really great opportunity to detect dark matter in some ways almost independently of the way that dark matter interacts. Okay, and so, you know, we're not necessarily constantly probing downwards in this parameter space looking for where the dark matter couplings are. We just have to look for this dark matter and its dynamical effects in this particular signature that's called dephasing, that I'll explain in a second. Okay, and so this is the very, very rough overview of what I'm going to say for the rest of the talk. So I'll start off kind of with, start off telling you about the systems that I'm interested in. Okay, the physical systems that I would like to see in gravitational waves, in the hopes of saying something about dark matter. Okay, and these things are called intermediate mass ratio inspirals. And as part of this, I'll kind of bring you up to speed on what the situation was, say 2 years ago or so, in the literature, and how we understood this this dephasing effect that I'll explain in a second. Okay, and then a lot of the talk will then be devoted into going in a bit more detail about this dephasing effect and how it's calculated, and kind of refining some of the calculations that went into this earlier work, which really changed the picture a lot, but which you really have to take these into account if you're ever going to hope to detect these signals and extract information about them, extract information from them. Okay, and in the last 10 minutes or so, I'll talk about more recent work where we go one step further and we think about what parameters you could extract from the dark matter by looking at these kinds of systems. Okay, and so the system, as I said, that I'm interested in predominantly is a so-called intermediate mass ratio inspiral. Okay, and this is essentially a central black hole, an intermediate mass black hole. So that's something that has a mass of 10 to the 3 to 10 to the 5, 10 to the 6 solar mass. And orbiting around this is going to be a smaller compact object, like a black hole or a neutron star. Okay, for now, we don't necessarily care about the nature of this smaller compact object. I'll sometimes just call it a neutron star because then it's easier to distinguish from this central black hole. But for most of this talk, it doesn't matter what that is. It just has to be some lighter compact object. And so if these systems are out there, then what would you observe in the gravitational waves that they emit? Well, as this orbit continues, energy will be lost through gravitational waves, which means that the system will start to spiral inwards, and that in turn will increase the frequency of the gravitational waves that are emitted because the orbital frequency will increase. And so what you see is kind of schematically a sinusoidal wave, roughly, which is increasing in amplitude as the two objects get closer, but also very slowly increasing in frequency. Okay, until you reach some final frequency at the innermost stable circular orbit of this object, at which point the two things merge. Okay, and here the gravitational wave strain that I've tried to illustrate here, something that I want to emphasize is that often you are really buried in a lot of noise. Okay, so you really need to know what this signal is going to look like. Okay, so looking here at this kind of frequency range where, I don't know, hertz or sub-hertz frequencies of gravitational waves. And so what we need to use to look for these gravitational waves is not a ground-based detector like LIGO, although I'll hopefully say a little something about that towards the end. But instead, it's a space-based detector like LISA, Laser Interferometer Space Antenna. Okay, and this system of essentially three test masses in space with a huge distance, millions of kilometers between these test masses, allows you to measure much lower frequency gravitational waves than you would with LIGO. Okay, and so we're down at the 10 to the minus 1, 10 to the minus 2, 10 to the minus 3 hertz. Okay, and so roughly speaking, well, this is something that really needs a lot of work still, but LISA could perhaps detect a few of these kinds of systems per year. Okay, and so we're starting to think this could be we might be able to see these systems, and so this is a promising thing to look at. But what we really need to detect dark matter is we need a lot of dark matter in these systems. Okay, and so what we want to think about is scenarios in which this central black hole, this IMBH, could amass a large overdensity of dark matter. And so one of the ways that this can happen is if this black hole, which forms, for example, from the collapse of an unstable gas cloud at relatively high redshift, if this intermediate mass black hole forms at the center of a dark matter halo, and if it grows very slowly, then you can really enhance the density of dark matter in that central region. Okay, and so for example, if you have this black hole forming at the center of an NFW halo, then you would expect to have a dark matter density profile with a slope which goes like with a power law slope with index 7/3. Okay, so this is a very steeply rising dark matter density, and if you plug in some numbers, you find that you can really reach densities which are huge. So sort of 10 to the 24 solar mass per cubic parsec in a very small region, but still a very huge density. Okay, so that's one possibility for forming these dense dark matter halos. The other possibility that we'll think about is in primordial black holes. Okay, so these are not black holes which form from the collapse of gas clouds relatively late in the universe or the collapse of stars. Instead, these are black holes which form from the collapse of large overdensities in the very early universe, okay, before the formation of the CMB, shortly after inflation. Okay, and if these things are real, then they will actually grow dense dark matter halos around them. And this is kind of simple to understand, because what happens is you have this very dense, you have a point mass, you have this primordial black hole, and then you have a universe around it which is gradually decreasing in density. And in that environment, the primordial black hole can essentially capture dark matter particles from this smooth background. Okay, and what you find is, again, a steeply rising dark matter density profile with a slightly different slope. Okay, and so the systems that we're thinking of are kind of these two, and I'll come back to these two benchmarks. One of them is this, what I've called here, this Astrophysical Benchmark, in which you have the formation of this intermediate mass black hole a little bit later in the universe, and I'll also mention briefly this PBH benchmark. Okay, and we can pick a couple of masses just to keep things concrete, but in general, this applies for a much wider range of masses. Okay, so now we have this system, we have an intermediate mass black hole, we have a neutron star or a smaller black hole, and a cloud of dark matter. Why is this interesting? Why is this relevant? And the reason is that there's an extra force now on the orbiting compact object. Okay, and it's dynamical friction. Essentially, this compact object, as it travels through a cloud of dark matter, can scatter the individual dark matter particles. Okay, or seen another way, you essentially produce an overdensity of particles behind the compact object as it passes through. Okay, and this is not a kind of particle physics scattering. This is purely a gravitational deflection, gravitational scattering. Okay, and the size of this dynamical friction effect traces the density of dark matter, and so hopefully, if you could map out this dynamical friction effect, you could understand exactly how much dark matter there is in these systems. And so, in practice, what this means is that you have an object which is inspiraling, It's losing energy through gravitational waves. Okay, so it's losing some orbital energy through gravitational waves, but it's also losing energy through dynamical friction. And what that means is it spirals in more quickly. Okay. In practice, looking at the gravitational wave strain, what you would find is that the system accumulates phase at a different rate. What I mean by that is, in some ways, observing gravitational waves is just about counting how many times this system orbits, and if you and counting how quickly it orbits. And if you have an extra source of energy loss, then the orbits happen more quickly. And the two systems, the system in vacuum with no dark matter and the system with the dark matter halo, can start to go out of phase, okay, because one of them is inspiraling more quickly than the other. Okay, it's accumulating cycles more quickly than the other. Okay, and this is the dephasing effect that I'm talking about. Okay, hoping to look for this distinction, this difference between a system evolving in vacuum and a system evolving with this cloud of dark matter. Okay, and so to put some concrete numbers on here, you could think about a system which starts, let's think of this astrophysical benchmark system starting at a separation of 10 to the minus 8 parsec. You know, it could start out much further, but around the time that we might start to observe it would be when it reaches a separation of about 10 to the minus 8 parsec. Okay, in vacuum, you would find that this system would merge from that point in about 5 years, and it would undergo about 6 million cycles. Okay, so it would orbit around roughly 6 million times. Okay, but then when you calculate the change in the number of cycles from some given starting frequency, or equivalently some given starting separation, up to the merger, you find that the change in the number of cycles due to this dynamical friction effect, due to this dephasing, can be huge. Okay, so if you look at 5 years of this inspiral, the change in the number of cycles can be a few million, okay, over 10 to the 6. But you started out with 6 times 10 to the 6 cycles, and so this is an order 1 effect. This could be huge. Okay, and so the hope is that you can discriminate between this vacuum system and this system which drastically changes the gravitational waveform just by making the system inspiral at a different rate. And from a particle physics point of view, or a beyond the standard model point of view, this is incredible because you can only get these very dense spikes in certain models. Okay, if you have ultralight bosonic dark matter, then you would find that depending on the de Broglie wavelength of these particles, they would not be able to produce very dense structures on small scales. Okay, so any observation of this spike would immediately tell you that you don't have dark matter, which is ultralight on some length scale. Okay, we know that light fermionic dark matter, the exclusion principle means you can't pack it into a very dense space, and so you would if you observe this dephasing effect, it doesn't make sense for that particle to be fermionic. And it's bad news also for the WIMP. If you observe this dephasing effect, then it doesn't make sense for the particle producing it to be a WIMP, because WIMPs will tend to annihilate, and so their density in the center of the spike will decrease, and it's not enough to give you this dephasing effect. And just very quickly, we came up with a kind of neat, slightly different idea concerning axions. Okay, and one of the cool things about axions, as I said, is that they can convert in a strong magnetic field into photons, and neutron stars can have extremely high magnetic fields. Okay, and so the picture that we envisaged, this cool idea, was that you could have a neutron star orbiting around this black hole, inspiraling towards the center. And as it inspirals, you would see this dephasing effect. You would see this gravitational wave strain accumulating phase at a slightly different rate. But also you would have these axions converting into photons in the strong magnetic fields of the neutron star, and you would potentially be able to see this emission of, in this case, it would be radio waves because of the particular mass of the axion. And so you would have this cool kind of dual observation that you could do. Okay, and so for example, observing these kinds of systems, you would be able to reach down to pretty low axion-photon couplings, depending exactly on the mass. But the nice thing is that you would not only be able to see, you kind of probe the coupling through this radio signature, but you would also be able to tell how much dark matter there is because of the amount of dephasing you would see. And so there's kind of a kind of degeneracy that gets broken here, which is very nice. Okay, kind of a cool and unique little multi-messenger probe of, in this particular case, of axion dark matter. So I think this dephasing is very exciting. If we can find it, then we can tell a lot about dark matter. First of all, it would be a detection of dark matter. It would tell us something about the nature of dark matter, and we might also look for some interesting sort of multi-messenger probes. The problem is that doing the whole calculation correctly is not easy. And it turns out that some of the things that I've told you already are actually wrong or not quite right. And so the rest of this talk will be about making those things right. Okay. And so I think this is probably a good time for a brief pause, intermission. And if anyone has any questions before we move on to the rest of the talk, now might be a good time to ask.
Maybe I can. Oh, Marcus has one. Okay, go ahead, Marcus.
Yeah, hi, Bradley.
Hi.
I had a question about this last point where you have a neutron star orbiting the black hole. So what sort of timescales are we looking at for the conversion into photons here?
So,
I mean, would this be a transient event or something which is emitting photons over a very long time?
So this would be emitting photons kind of continuously over a long time, and the idea would be that as it inspirals, it sort of experiences a higher and higher dark matter density, and so you would get more and more photons coming out. The flux would increase. So and I think the sorts of timescales we're thinking of here is over the course of years to do the inspiral.
Okay, thank you.
Does that answer? Yeah.
Okay.
Yeah. And Enrico, please go ahead.
Hi, just a curiosity. So I was wondering how, if the presence of an accretion disk or matter surrounding the black hole might change your prediction on the dynamical friction.
Yeah, no, this is a great question, and this is something we need to think of more carefully. An accretion disk or any kind of, I mean, you could imagine like a baryonic cloud would give you a very similar effect. The hope, which we haven't managed to show yet, and I'll get into this a little bit more later, is that the exact shape of the gravitational waveform will allow you to map out the shape of the overdensity. And if you can do that, you can hopefully disentangle, a baryonic mass distribution, which you might expect to be a kind of flat accretion disk. You might be able to disentangle that from a more spherical and much more dense dark matter halo. And so baryons should give you a similar effect, but it should be subtly different. And the hope is that you should be able to disentangle those two things.
Oh, okay, cool, thank you.
Yeah. Okay.
So I have a question, Bradley. So you're saying that the change in the number of cycles can be up to some millions, right?
Yeah.
I think it's like 16. Okay. But maybe I'm wrong about this, but my understanding is that we only see in gravitational waves, the last bits of the inspiraling. So we don't see millions of cycles at the end. We see a few.
So that would be the case with, for example, LIGO, where the frequency range that you're observing over effectively corresponds to the last, say, 10 or 100 cycles of the inspiral. What I'm thinking of here is actually much lower frequency, and so for example, Lisa might be able to detect, it might have its peak around 10 to the -2 hertz, say. And so the frequency range that you observe over actually corresponds to a lot of cycles of the binary, a lot of orbits of the binary. Does that make sense?
Yeah, so it's like a longer monitoring campaign of the object. Okay.
It's both a longer monitoring campaign and also a kind of slower evolution in frequency.
Right.
Yeah.
Right. Yes. Thank you. Enrico, I think that's your old hand. Right? So I think there's no more questions. So please, Bradley, go ahead.
Okay. Thank you very much. Great. Let's. Okay. So if there are no more questions, I can go on to tell you about how a lot of what I just said was completely wrong by kind of going back and revisiting some of these calculations. And the first thing that we noticed was if you want to produce this dephasing signal, you need a lot of energy. Okay, you can calculate how much energy the system essentially loses through this dynamical friction effect. And you can ask, where does this energy come from? And it has to come from essentially the binding energy of the dark matter. Okay, you have to inject energy into this sphere of dark matter and kind of puff it up and perhaps even expel some of the dark matter. And what you can do is you can calculate basically the binding energy that's stored in this sphere of dark matter, in this dress, in this halo, and compare it to the amount of energy that you're trying to do with dynamical friction when you do this calculation. Okay. So what you find is that actually the amount of energy that you would need to successfully do this inspiral, or to successfully speed up the inspiral by the amount that you're trying to, is actually much larger than the amount of binding energy in the dark matter halo. Okay, in other words, we're assuming that this system is just static, and that the amount of energy that's injected as the smaller object spirals in is very small. But it turns out that the amount of energy that's injected by the inspiraling object is actually very big compared to the amount of energy we have available in this gravitational binding energy. And what that means is that the calculation doesn't make sense anymore. What will happen is that this system, this halo of particles, will respond in some way. Whoops, that came out a little wrong. But as a kind of first estimate, what we can do is, let's say this dynamical friction effect is 100% efficient. It can extract all of the binding energy from this halo of dark matter. Okay, and so what you can say is, you can say that means the maximal dynamical friction force I can get is just given by the amount of energy that I can sort of suck up as I spiral inwards. And when you do that, you find that the size of this dephasing effect is actually much, much smaller than you thought it was going to be. Okay, and so immediately we should be thinking, this original calculation can't possibly be right. It doesn't even conserve energy. Okay, and so what we need to do is we need to include the dynamics of the dark matter halo in this calculation. And so I did what any self-respecting person does, which is I started trying to do some numerical simulations, some n-body simulations. I said, let's have a central massive black hole, a smaller black hole, and then a bunch of dark matter particles. Okay, and see how this system evolves, see whether you can see the disruption of the dark matter halo. There were some technical issues. You're trying to trace changes per orbit at the level of 1 part in 10 to the 4 or 1 part in 10 to the 5, and so I had to track down a very annoying issue in gadget 2, which was some incorrect digits in Newton's constant, but that's just how it is. And so these are some of the results that I had from these numerical simulations. Okay, so here I'm showing the change in the fractional change in the radius of the orbit as a function of the number of orbits. Okay, and each different colored line is just a different random initialization of the data of the system. And as you can see, this system is slowly decaying. Here, I don't have any gravitational wave emission. I just have this dynamical friction force. The system is very slowly decaying, but this corresponds to a time scale for the system of about 3 days. And in fact, this was taking about 3 days to run. And so this is not really a feasible way to do this. Maybe there are better ways, and this is something I'd like to investigate in future, but I don't think I want to run this whole thing for 5 years to see what the system looks like at the end. One thing that's helpful is that these simulations can actually help us normalize the dynamical friction force. There's a Coulomb logarithm term which encodes how far away the particles need to be before their interactions with the black hole are not relevant anymore. And these simulations turn out to be useful for fixing that, but that's kind of another story. And so what we did in the end was to say, let's try and treat this semi-analytically. Let's say we have a sphere of particles, it's a gravitating sphere of particles, which is supported by the gravitational potential psi of the central black hole. And the distribution of these particles, F, the distribution function, is just determined by the energy of the particles. Okay, and this kind of, here I'm writing this as a kind of relative energy, so it has some flipped signs, but essentially this epsilon just captures the energy of the particles in the halo. And what happens is that as particles pass near this smaller object, they receive a kick, and so they go to a different energy. Okay, and that kick is purely just the energy they get from passing nearby and being kind of slingshotted away. Okay, and if we know the distribution function for these particles, then we know the density. We can reconstruct it by integrating over all the possible velocities that the particles can have. Okay. And so the equations that we used look like this, but you can really understand them in relatively simple terms. So the change in the distribution function over one orbit corresponds to the chance that a particle scatters if it has a particular energy times the number of particles which have that energy. Okay, so these particles and that's fine. This factor here is essentially a phase space factor, because there are more states at one energy than there are at another. But this is essentially what we have to do. Okay, and if we're interested instead, not in a per orbit, but in a kind of instantaneous derivative of the distribution function, then we can do that quite easily just by multiplying by this orbital timescale. Okay, and then the last part is just to calculate the probabilities for scattering. What's the likelihood of a particle scattering with this small compact object? And essentially you can do that by calculating what fraction of particles lie within this torus, which is defined by the radius of influence of the small black hole. Okay, if a particle lies inside that torus, then it's close enough to interact gravitationally with the small black hole, and this radius of influence is set and kind of calibrated using the n-body simulations that I talked about earlier. Okay, the kind of detailed formalism is in the paper, and there's some code that's available online to actually to do this. But essentially, that's what you have to do. You have to shuffle particles between different energies, and the question of which particles get a kick, or which energies get a kick and which don't, is determined by which particles lie within this sphere, this radius of influence, this torus of influence. Okay, and so what you get is something like this. If you look at how the density profile of dark matter evolves as a function of time. Okay, and so here I'm fixing the orbital radius of the small object. So I'm allowing it to orbit, but I'm not allowing it to inspiral at all. I'm just kind of setting up like a test case where I'm just injecting energy into the halo, and I don't care about the rest of the system. And what I find that happens is, as I inject energy, I increase the orbits of these particles. Okay, and so I deplete particles from one particular radius. Okay, so going from red to blue, I'm going from more and more time of the compact object orbiting. Okay, and so I'm depleting, but those particles then get pushed up to a larger radius. Okay, and in fact, it's hard to see from here, but some of those particles will be completely ejected from the system. Okay, there's a kind of subtlety here that I'm plotting only the slow-moving particles. By slow-moving, I mean particles which are moving more slowly than the local orbital speed. Okay, these are particles which are moving more slowly than the compact object would be at that radius. And it turns out these are the particles which participate in dynamical friction, or they're the ones which are most relevant for calculating this dynamical friction force. Okay, and this behavior, this kind of depletion of the density and kind of moving things out to larger radii, in my head, it always just makes me think of driving through a puddle, and you inject energy into the puddle and the puddle sprays out somewhere else. And in the process, your car has to slow down a little bit. And in our situation, that slowing down is the dynamical friction, which makes you inspiral a little bit quicker. Okay, so now let's kind of couple all of this together and see how the combined system evolves. Okay, so here we have this dashed line shows you the position of the small compact object. And then this red line is all of the particles which are moving slowly enough to be relevant for dynamical friction. Okay, and if I start this, what happens is that very quickly the particles begin to be depleted. The object starts to spiral in under both gravitational wave emission and this dynamical friction. But then what happens is at each radius, more particles get pushed out and out and out. Towards the end of the inspiral, it turns out that the gravitational wave emission dominates. And so this dynamical friction effect is not such a big deal anyway. But the most important thing to take from this is that the instantaneous density that the small black hole sees is much, much smaller than you would expect without this feedback, essentially, without the dynamics of the dark matter halo. Okay, so you have this compact object which is injecting energy into the system, depleting the particles nearby, and therefore it experiences a smaller density and so a smaller dynamical friction effect as it inspirals. And we can then translate that into this kind of heuristic that we're using, which is the change in the number of cycles as a function of, well, starting from some particular frequency or starting from some particular separation. Okay, and so we had this idea of a static dark matter halo, which would give us a huge dephasing effect if we observed over 5 years, which would be millions of cycles. In reality, taking into account the dynamics of the dark matter halo, this is much, much smaller. It's something like 100 times smaller size of effect, including the dynamics of the halo. You can also look, for example, at one of the effects here is that the system then takes less time to merge because it obviously has to do fewer cycles. It spirals in more quickly. And so in the static case, you would expect that this merger, which happens when this line goes vertical, would happen over a year earlier than in the vacuum case without dark matter. In reality, what happens when you take into account the dynamics of the dark matter halo is that you have a merger which is much closer in time to what you would expect in the vacuum case. Okay, and again, this is like a factor of 100 or so smaller effect. Very briefly, if you have a larger central mass, it turns out the difference between this static approximation and the dynamic approximation, so this blue and this red curve, the correction between those two is smaller, precisely because you have a more massive object in the center, which kind of supports it keeps the halo in place. That's one way to think of it. Another is that the amount of binding energy, the gravitational binding energy, is much larger because you have this more massive central object. Okay, so the mismatch between this static and dynamic case is a bit smaller. And so this looks like bad news, right? We've decreased this huge and obvious signal from an order 1 effect down to maybe 1% or a per mil level effect. And even if we say, well, for heavier objects, this is a smaller correction, actually, we need to have very, very precise waveforms if we want to do this well. So we need to do this. We need to take these things into account. The good news is that people use as a kind of rule of thumb that LISA should be able to detect a dephasing as small as 1 radian or maybe 1 cycle. And so we still have a little bit of hope to be able to actually detect this effect. And so in the last 10 minutes or so, I'll talk about trying to do precisely that, trying to ask, can we actually measure this, detect it? What would we go about doing in a real scenario? And so the real scenario that I'm talking about is that imagine you can detect this waveform. Okay, so you see some event, you see a merger, or you see some coherent gravitational wave, and you have no idea the properties of the system behind it. You don't know the masses, you don't know the dark matter density, you don't know whether there is any dark matter. Okay, and so it's you have to ask, can I distinguish between, well, first of all, how near does this thing have to be loud enough to detect? Can I distinguish a system which has this dark matter dephasing from a system which doesn't? And then if I can tell that there is dark matter, what can I say about the dark matter halo in that case? Okay, and so I'll address these 3 things in the last 10 minutes or so. So the first one is pretty easy. Basically, we should be able to detect this system with LISA if the signal to noise ratio is large enough. Okay, and essentially that means how close do we have to look to be able to detect these things? And the signal to noise we estimate using what's called the match between 2 waveforms A and B. It's essentially the product of the Fourier transforms of the 2 waveforms, weighted by the signal, weighted by the noise curve of LISA as a function of frequency. Okay, so this upweights regions of frequency where LISA is very sensitive. Okay, and this basically is just a way of determining whether 2 waveforms look similar. And then the SNR is just taking a particular waveform and calculating the match with itself. And what we find, looking at systems that we've been talking about so far, is that if you have a chirp mass around 17 or 18, which is this benchmark that we've been talking about, you need to be within about 75 megaparsec to be detectable with LISA with an SNR of 15. So I would love to be able to give you a more concrete idea of exactly how many events we expect to see in that kind of sphere in which they would be detectable. That encompasses the Virgo supercluster, so we would hope that there would be ample opportunity. But as I'll say later, there's a lot of work that still needs to be done to determine exactly how many events we would expect to see in that kind of sphere. So the question of discoverability is now the next thing. So this is, I'm calling a system discoverable if we can distinguish it from a system with no dark matter. And the way that we do this is by calculating the Bayesian evidence for these different models. Okay, so we hop around parameter space, where parameter space is for the vacuum case, we just have a chirp mass. Okay, so we try and fit different waveforms with different chirp masses to the data. In the dynamic case, in the dressed case with dark matter, we have the properties of the spike, so the slope and normalization, the chirp mass, but also the mass ratio. It turns out that the mass ratio also affects the shape of this waveform. Okay, and so there are also some extrinsic parameters to do with the distance to the source and the phase and time of coalescence, but it turns out you can do some tricks to kind of push those to one side, so we won't worry too much about those. And so what we do for each of these two possible models is we have some observation, and we calculate the Bayesian evidence. Okay, so we integrate the likelihood, which is related to this match that I described earlier. How close to the two how close does the data look to the waveform at this particular point in parameter space? And we weight by the prior, and this integral tells us something about, well, it should tell us something about how likely, how much we should believe this particular model. And then we can calculate the Bayes factor, which is the ratio of these two Bayesian evidences. Okay, and if this is very large, then we should prefer this D model with a dark dress with a dark matter halo. And if it's very small, then we don't necessarily prefer one over the other. Okay, so what we find is the following. So on the left here, we have the colors that I'm plotting are the difference, essentially the total dephasing over 5 years. Okay, so this is what I was showing you in some of these previous plots. This is kind of a heuristic for the size of the dephasing effect. Okay, as a function of the normalization of the spike and the slope. Okay, the problem is that really this is not a good measure of how big the dephasing is, because if you see some signal, you don't know what the vacuum system looks like. Okay, you cannot compare the system with a dark dress with this dark matter halo and the system in vacuum, because you don't know what the system in vacuum is. So instead, on the right, we plot the difference in the dephasing between essentially the data, this dark dressed system that we observe, and the best fitting vacuum waveform. Okay, and what you find is that it's in some parts of parameter space over here, it's just a few cycles difference over the whole inspiral. And then in all of this white region, it actually just becomes too hard to find the best fitting vacuum waveform. There aren't any good vacuum waveforms that fit. And these black lines show the Bayes factor. Okay, this kind of measure that we're using to determine whether we should prefer one model over the other. And we find that very, very quickly, you find huge Bayes factors in favor of this dark matter halo system. Okay, and the benchmarks that I've been talking about so far, so an astrophysical benchmark, a kind of reasonable astrophysical benchmark would lie way over here, and this primordial black hole benchmark for the formation of the central black hole lies all the way over here. So these things would certainly be distinguishable from just a kind of solo vacuum system with no dark matter. Okay, no vacuum system would look like these systems that we're looking at. Okay, and the final thing is measurability. I mean, if you now are convinced that there's dark matter here, you can go in and try and reconstruct the parameters of your system. Okay, and so you can reconstruct the slope of the dark matter density profile, the normalization, chirp mass, and the mass ratio Q. Okay, and you know, you can get some tight correlations between some of these parameters. That's fine. This is all, you know, looking very nice. The real question, or the interesting thing to ask, is what can I learn from measuring these parameters? Okay, and so we'll focus for a second on this this one here, the slope of the density profile. Okay, and so this is what I reconstruct for the slope of the density profile in if I have my data as the astrophysical benchmark, And on the right, I have this primordial black hole benchmark. Okay, and these have two different values, or two different expected values for this, this slope of the density profile. And what I find is that I can also discriminate between the two models. Okay, so this 2.25 lies all the way over here. So it, my astrophysical system looks nothing like my primordial origin system. And this 2.333 is all the way over here, and so vice versa. Okay, and this is something we didn't understand or didn't know at the start, that you can, not only can you hopefully distinguish these systems from any kind of vacuum system, but you should also be able to distinguish them from each other. And in this case, what that means is you should be able to say something about the origin of the dark matter spike and how it formed. And also it gives us a bit of hope for very precisely measuring the slope and the shape of this dark matter halo in order to differentiate different dark matter models, which might produce slightly different shapes of slope. And in fact, the question that we had earlier about baryonic accretion disks, for example, hopefully, because we can so precisely measure these parameters, we should, or this is something that needs to be demonstrated, but we should be able to distinguish a particular slope or a particular shape of dark matter halo from a particular shape of accretion disk. I think that's kind of the situation as it stands now. And so there's a huge amount of interest in this and related topics. And so I should definitely thank many of my collaborators. These are some of the key ones here who are working on this and kind of interrelated projects. And the reason that there are so many interrelated projects is that there's so much that we feel that we still need to do here. So for example, everything I've done so far has been in the Newtonian approximation. So I'm thinking of kind of Keplerian orbits of the black holes. It turns out that intermediate mass ratio inspirals, that doesn't work at all, and you have to do something more complicated. It turns out to be very hard to actually solve this system fast enough to give you lots and lots of waveforms, right? And so one thing that we're thinking of doing is kind of building a waveform generator that's fast, that uses maybe some machine learning techniques to generate waveforms without us having to solve the whole system slowly everywhere. And then a lot of what we're trying to do at the minute is to understand exactly how many of these systems there should be out there. Okay, how many of them, how many black holes form in the right conditions, in the right places, how many of them live in environments where you don't have a lot of mergers or you don't have a lot of baryons to screw up this nice dense spike. And another thing is that we're thinking about whether or not any of this is feasible to detect with ground-based detectors. And so, well, people can ask later, but it turns out that if you have two primordial black holes, one of them could be very, very light, so on the order of 10 to the minus 3 solar mass. The other could be about 5 solar mass. And it looks like this kind of system could be detectable with LIGO or Einstein telescope. And you can start to maybe reconstruct some of the parameters of this system. Okay, so maybe we don't need to wait quite as long as I had initially claimed. You don't have to wait until the 2030s for LISA. If primordial black holes are out there with this particular mass distribution, we might be able to detect them in this way with the dark matter that's around them. But if anybody is interested, we can talk a little bit more about that. Okay, so I think this is it's a very interesting, to me, it's a very cool problem, partly because there's so much physics that needs to be modeled so carefully. Okay, and when you start to do that careful modeling, you find that you can have this huge correction to the kind of 0th order estimates that you come up with. There's lots of calculations that still need to be done in modeling and trying to build template banks that you would realistically be able to use and to understand exactly how realistic some of these systems are. But I think the possible gains are huge, right? If you detect this spike, it tells you something about dark matter. And maybe you can also think about more exotic multi-messenger signatures, looking at radio emission and gravitational waves, and maybe even other things. But for now, I think I'll stop. And if anybody has any more questions, I'm very happy to answer.
Thank you so very much, Bradley. This was super interesting.
Thanks.
Do we have questions in the audience? There's a lot of clapping. Always good.
That's good. That's good. It's better than booing.
Yeah, it was good. So let me ask you one question. So in your slide 44, you were showing the Astro versus PBH.
Yeah,
that one. Yeah, and that to me is striking. My guess is that the errors that you're showing there for the gamma sub S are 68%, right?
Yes, they're 68%, but yeah. I think you can kind of see from the posteriors the actual kind of curves, which are a little bit noisy, but you can see that it very quickly drops.
Yeah, it's very peaked.
Yeah.
So my question is there any fudge factor here? For instance, the PBH benchmark, could it have some extra astrophysical uncertainties that could actually mimic what you're seeing on the left? I'm other than the baryonic lit disk that you were talking about, something extra.
So there's nothing that comes to mind. So the nice thing about the PBH case is that the physics of the formation of the dark matter spikes around PBHs is now very well understood. Like it's all early universe physics that you can solve quite easily and quite convincingly, and so there isn't a lot. There's not a lot that you can do on the right hand side here to change things. And so, yeah, in fact, it's both the density and the slope are pretty much fixed on the right. The issue is that on the left, really things are a bit more sketchy. And we picked kind of one point, which is the historical point in parameter space that people have looked at. And it just so happened to be distinguishable from the PBH case. We really need to, going forward, be a bit more careful and think a little bit more carefully about what kind of systems would have realistic parameters. Does that answer your question?
Yeah, that answers the question. Thank you.
Okay.
We have time for one final question, and I see one from Jonathan. So please, Jonathan, go ahead.
Yes, I noticed that you were talking about a Taurus of influence, and I wondered why this isn't a sphere of influence.
Yes, sorry, I skipped through that a little quickly. So the idea is that so if you imagine this small compact object, yes, it has a sphere of influence, but over one orbit it traces out a circle, and so essentially it's lots of spheres of influence added together to create a torus of influence.
Oh, I see. I thought it would be a small torus around the small black hole, but that makes sense. Thank you.
Yeah. Yes, sorry about that. It's a very confusing. I did more geometry for this paper than I was expecting.
No, what you said makes sense.
Okay,
so
cool.
I don't see any more questions. So Bradley, thank you so very much. We were happy to have you here. I hope we can have you in person in a not very distant future now.
That would be fantastic. Thank you very much.
And thanks, everyone. I think we have an extra seminar next week, and you'll get an announcement for that. So thanks, everybody, and see you in 1 week. Okay, bye-bye, Bradley. Bye-bye, everyone.